8%. That is the humidity forecast for 9 western states tomorrow morning. The Sahara Desert averages 25. Death Valley in August sits around 10. And somehow, in March, the American West will be drier than both of them simultaneously, while 70-mile-per-hour winds begin moving across the same terrain. The March 2026 heatwave did not end. It quietly transformed into something the federal fire agencies have never described in language like this early in the year, something they are visibly uncomfortable naming. Stay with me until the end. Because what this heatwave became, and what it is about to trigger, is considerably unsettling. If this has you hooked, subscribe to the Sky Lab and tell me honestly, a heatwave drier than the Sahara, snowpack at the lowest levels ever recorded, federal agencies using language they have never used in March, and a pre-ignition environment sitting across 9 states waiting for a single spark. All of it converging on one weather window. If that is not the atmosphere clearing its throat to get our attention, what exactly is it? Now, let's get into it. Part 1. The 12-hour window that changes everything. Here is something that should not be possible in March. Tomorrow, across 9 western states, the relative humidity will drop to 8%. Not 15, not 12, 8. To put that number in context, the Sahara Desert, the place we collectively use as shorthand for uninhabitably dry, averages somewhere between 20 and 25% humidity. Death Valley in the middle of summer, one of the hottest places on the surface of this planet, sits at around 10. And tomorrow, a stretch of the American West covering Wyoming, Colorado, Nebraska and New Mexico will be drier than both of those places, in March. While most people are still thinking about whether they need a light jacket, that number alone would be enough to get meteorologists on the phone with each other. But 8% humidity is not even the full story, because at the same time that moisture is collapsing out of the air, winds will be sustaining at 30 to 40 miles per hour, with gusts climbing to 70. And temperatures will be sitting at levels that, 3 weeks ago, shattered every record this country has ever recorded for the month of March. What you are looking at is not one bad thing happening. It is 3 bad things happening simultaneously, in the same place, at the same time. And that synchronization, that is what separates an uncomfortable weather event from something meteorologists describe in language they almost never use this early in the year. The National Weather Service has issued language stating, and I want to be precise here because the wording matters, that fires will catch and spread rapidly and erratically. Rapidly and erratically. That is not a standard phrase pulled from a template. That is the kind of language that gets used when the people running the models are looking at outputs that make them uncomfortable. 13 red flag warnings are currently active, and that number is still expanding. The Storm Prediction Center has designated critical fire weather risk across a significant portion of the country. These are not routine classifications. These are the system's way of raising its hand. But here is what I want you to hold on to as we go through this, because this is the thing that keeps getting buried under the weather statistics. What we are watching is not a fire event. Not yet. What we are watching is what scientists sometimes call a pre-ignition environment. The conditions for catastrophe exist completely independently of the catastrophe itself. The air is already there. The wind is already there. The dryness is already there. Everything that a fire needs to become something uncontrollable is sitting in place across hundreds of thousands of square miles of American terrain, and the fire has not started yet. There are currently 192 active weather alerts across the United States. 192. That is not a single storm. That is not a regional anomaly. That is a system-wide signal, and it is the kind of signal that suggests something has shifted at a scale larger than any individual weather event can explain. When you zoom out far enough, the pattern stops looking like weather and starts looking like something else entirely. Think of it this way. There is a concept in fire science called the pre-ignition environment, and it describes exactly what it sounds like. The state of an environment before fire touches it, when all the variables have already aligned and the only missing ingredient is a spark. The fuel is ready. The oxygen supply has been turbocharged by wind. The heat has already done its work on moisture levels. The environment is not waiting for conditions to get right. The conditions are already right. The environment is waiting for an event. And here is where it gets genuinely unsettling. When the National Weather Service says fires will catch and spread rapidly and erratically, that word, erratically, is doing a lot of work. It means that standard fire behavior models, the ones trained on decades of observed data, start to break down under these conditions. It means that the direction a fire moves, the speed at which it jumps terrain, the way it behaves around populated areas, all of that becomes significantly harder to predict. And when you cannot predict fire behavior, you cannot position resources ahead of it. You are always reacting, you are always behind. So the question I want to leave hanging in the air as we get into this is not whether fire weather conditions tomorrow are dangerous. They clearly are. The question is, what kind of system produces a pre-ignition environment of this scale, this early in the year, across this much of the country simultaneously? Because the answer to that question is not found in tomorrow's forecast. It is found in everything that happened in the weeks and months before it. And when you start pulling on that thread, the picture that emerges is considerably stranger than a heat wave. What happens when the environment becomes the fire before the fire even starts? Part 2. The anatomy of a perfect firestorm. Let me walk you through what actually happens physically when a fire starts under conditions like these. Fire is, at its most fundamental level, a chemical reaction. You need three things: fuel, oxygen, and heat. Remove any one of those three things and the reaction stops. This is why firefighters use water. They are cooling the fuel below ignition temperature. It is why fire breaks work. You are removing the fuel. It is why smothering a flame with a blanket cuts off the oxygen. The triangle is simple. What makes a fire catastrophic is not the triangle itself. It is what happens when all three sides of that triangle are pushed to their absolute maximum at the same time. And that is precisely what is being set up for tomorrow. So let us go through each side. Fuel first. The vegetation across the affected states, the grasses, the shrubs, the accumulated dead plant material from previous growing seasons is sitting at moisture levels that fire scientists describe as explosive. At 8% relative humidity, vegetation loses its internal moisture at a rate that most people would find alarming if they could see it happening in real time. The cells inside plant material are essentially dehydrating under the low humidity, and when plant moisture content drops low enough, ignition becomes almost trivially easy. The important distinction here, and this is something that gets missed in casual coverage of fire weather, is that desert plants are adapted to this. The vegetation that evolved in genuinely arid environments has biological strategies for surviving chronic low moisture. The forests and grasslands of Colorado, Wyoming, and Nebraska did not evolve under those conditions. So when desert-level humidity shows up in those environments, the fuel responds the way unprotected tissue responds to extreme heat. It becomes receptive, and that connection between moisture collapse and ignition risk is at the core of why this event is so concerning. Now consider oxygen. Wind is essentially an accelerated oxygen delivery system for a fire. At 30 to 40 miles per hour sustained, a fire receives a continuous, forceful supply of fresh oxygen to its combustion zone. This does not just make the fire burn hotter, it makes it burn faster, significantly faster, but gusts to 70 miles per hour introduce something even more consequential. At that speed, wind physically carries burning embers, firebrands, in the technical language, miles ahead of the fire's main front. This is called spotting, and it is one of the primary reasons fires under extreme wind conditions become nearly impossible to contain. You can throw everything you have at the main fire line and lose the battle entirely, because the fire has already relaunched itself from an ember that travelled 2 miles in 30 seconds. At 70 miles per hour, you're dealing with Category 1 hurricane wind speeds. In a hurricane, that wind moves water and debris. In a fire environment, that wind moves fire itself. And then there is heat, which brings us directly back to the central story here, because the heat is not new. The heat has been here. The March 2026 heat wave that pushed temperatures to 112 degrees Fahrenheit across parts of the American West did not end when the most extreme temperatures passed. It lingered. And during the weeks it lingered, it was doing something that is easy to overlook but is arguably the most important part of understanding what tomorrow represents. It was running a continuous extraction process on every soil layer, every plant, every patch of ground across a multi-state region. The heat acted as a drying engine, slowly, day after day, pulling moisture upward and out of everything it touched. This is why the fuel is in the state it is in right now. The heat wave did not simply make things warm, it made things ready. When you combine fuel at explosive moisture content, oxygen delivery turbocharged by hurricane-force gusts, and a heating process that has been running continuously for weeks, you get what fire scientists call a self-propagating fire system. This is a fire that generates its own favourable conditions as it burns. As a large fire grows, it creates its own wind patterns, it draws air inward toward the combustion zone, and pushes superheated gases upward in columns that can reach tens of thousands of feet into the atmosphere. A large fire, in other words, actively works to sustain and intensify itself. It stops being a fire and starts behaving like a weather system. There is an analogy used in structural fire science called flashover, and it describes the moment in a burning room when the accumulated heat from a small fire reaches a threshold where every combustible surface in the room ignites simultaneously. The room does not just burn, the room becomes fire all at once. What fire scientists observe under conditions like the ones forecast for tomorrow is something functionally similar at landscape scale. Not a flashover room, a flashover landscape. When the fuel is prepared the way it has been prepared, when the dryness is as extreme as 8%, when the winds are supplying oxygen at the rate 70-mile-per-hour gusts supply it, the fire does not spread the way a fire normally spreads. It propagates, it jumps, it behaves in ways that surprise even experienced incident commanders. And this raises a question that I think is worth sitting with. At what point does a wildfire stop being a fire and start behaving like a storm? Because the answer to that question has very practical consequences for the people whose job it is to stop it. Part 3. Red flag warnings are not the story. 13 red flag warnings. That is the number currently active as tomorrow's conditions align, and if you follow fire weather at all, that number sounds significant. It is significant. But I want to make the case that 13 red flag warnings is not actually the headline here, and understanding why requires a brief look at what that classification actually means and what sits above it. A red flag warning is issued by the National Weather Service when a combination of conditions, typically low humidity, high wind and dry fuel, creates elevated fire danger in a specific area. It is a real warning. It is not routine. But it is also, in the current climate reality, issued frequently enough that it has become part of the background noise of fire season. What sits above it in the classification system is a designation from the Storm Prediction Center called Critical Fire Weather Risk, and that is what has been issued for tomorrow. Critical Fire Weather Risk covers a broader geographic area, integrates more data streams, and represents a higher level assessment of atmospheric conditions. It is the Storm Prediction Center telling the country this is not a localized concern. Now add to that the dry thunderstorm risk. A dry thunderstorm is almost a philosophical paradox, a storm that generates lightning without generating rain. The rain evaporates before it reaches the ground in extremely dry air columns. So you get the ignition source without the suppression mechanism. It is as if the atmosphere found the one way to make the situation worse and decided to use it. Dry thunderstorm activity is being flagged across portions of the affected region, which means that even without any human-caused ignition, the sky itself is capable of starting fires tomorrow. But here is the part of this story that deserves more attention than it is getting. The fire alerts are not just in the west. When you map the current fire weather warnings across the country, you find elevated risk reaching into New York, into Georgia, into states that most people would never associate with serious wildfire danger in late March. This is genuinely anomalous. Fire risk in the United States is typically a regional story, a western story most years, concentrated around specific terrain types and specific seasonal windows. A continental fire risk pattern, with alerts running from the Pacific to the Atlantic, suggests that the atmosphere is not producing a regional weather event. It is producing a systemic one. This connects directly back to what we are really examining here, which is the question of how a heat wave that seemed to peak and pass actually transformed into something structurally different. The record temperatures of March 2026 did not create one dangerous area. They apparently primed an entire connected atmospheric system. Think about what that means for the traditional way we talk about fire season. Fire season in the American West normally begins somewhere around June. The language used by the National Interagency Fire Center for this event uses phrasing like fire behavior not typically seen in March. That is institutional understatement. What they mean is that the conditions they are observing belong to a different time of year. When a system generates continental-scale fire risk in late March, you are no longer asking a question about regional weather patterns. You're asking a question about whether the atmospheric system as a whole has shifted in a way that makes the old seasonal calendar unreliable. And that question does not have a comfortable answer. If this is happening everywhere at once, what changed in the system itself? Part 4. The heat wave that refused to die. On March 26, 2026, a weather station in the American Southwest recorded a temperature of 112 degrees Fahrenheit. In March. That is not a statistic that needs much contextualization. Your body knows that number is wrong for that time of year. But the true scale of what happened requires looking at the full picture. 14 states broke their all-time March temperature records in a span of days, not their records for that particular week or that particular date on the calendar. Their all-time records for the entire month. Over 1,400 daily temperature records fell across the country in that same window. The World Weather Attribution Project, which conducts rapid scientific analysis of extreme weather events to quantify the role of climate change, assessed this event and arrived at a number that is worth saying slowly. This heat wave was approximately 800 times more likely to occur in the current climate than in a pre-industrial climate. 800 times. That is not a marginal shift in probability. That is a fundamental change in what the climate system is capable of producing. The mechanism that made this possible is what meteorologists call a heat dome, a persistent high-pressure ridge that acts like a lid over a region, trapping warm air beneath it and preventing the normal atmospheric circulation that would dissipate the heat. Under a heat dome, the air that descends into the region warms further as it compresses. Days pass, the lid stays, temperatures climb. Most heat domes eventually break down as the ridge shifts or weakens, and the region returns to something closer to seasonal normal. That is what everyone was waiting for, and in a technical sense that is what happened. The most extreme temperatures moderated, the ridge weakened, the 112-degree reading stopped, but the heat wave did not end, it transformed. And this is the distinction that I think is the key to understanding everything happening right now. Here is what persistent warmth does to an environment even after the peak temperatures pass. Every day that temperatures remain above normal, even 10 degrees above normal, which sounds mild after 112, the sun and the dry air continue pulling moisture out of everything they touch, out of the soil, out of the vegetation, out of the accumulated organic material on the ground. This process does not stop when the record temperatures stop. It slows down slightly, but it continues, and it has been continuing for weeks. The most useful mental image I can offer is this. Imagine leaving a damp sponge under a heat lamp. The lamp does not have to stay at maximum setting for the sponge to eventually become completely dry. It just has to stay on. If you leave it long enough at any elevated temperature, the sponge will lose every drop of stored moisture until it is brittle. The American West has been sitting under a heat lamp since early March. The soil moisture, the plant moisture, the accumulated water content of everything in the ground, it has been systematically extracted day after day. What remains is fuel, everywhere. As far as the relevant fire weather models can see, this is what meteorologists mean when they describe what is happening as a drying engine. The heat wave, even in its diminished form, has been running an extraction process on the entire region, and that process has now produced the conditions for tomorrow's critical fire weather event. The heat was the first act. The fire weather is the second. And understanding that sequence, understanding that the heat wave did not end, it evolved, is essential to understanding why 13 red flag warnings and critical fire weather risk designations are appearing in late March instead of July. What if the real danger of heat waves is not the heat itself, but what the heat leaves behind? Part 5. Monday is not the beginning, it is the trigger. As of right now, widespread fire activity across the affected states is limited. If you pulled up the satellite fire maps this morning, you would see a relatively quiet picture. Scattered hotspots, nothing resembling the kind of large active fire complex that fills news coverage. And that quietness is deceptive in a way that I want to spend some time on, because it is precisely the kind of calm that experienced fire managers find most uncomfortable. There is a concept in fire science sometimes called the ignition gap, and it describes the temporal space between when conditions become catastrophic and when ignition sources actually align with those conditions. conditions can be maximally dangerous and produce no significant fires for hours or even days, not because the danger is not real, but because the spark has not arrived yet. The environment is fully prepared, the trigger has not been pulled. Think about what actually starts wildfires. Power lines, when wind causes them to contact each other or contact vegetation, they produce arcs that can drop fire directly into dry grass. Vehicles, exhaust systems, and mechanical sparks on roadway margins account for a significant portion of fire starts in high-traffic areas. Human activity in general, discarded materials, escaped debris burns, equipment use, and lightning, which in a dry thunderstorm environment, as we discussed, arrives without rain to suppress what it starts. Every one of these ignition sources is going to be present tomorrow. The wind that creates dangerous fire spread is the same wind that will stress power lines. The roads that cross the affected terrain will carry vehicles. The atmosphere is going to generate lightning. The gap between conditions and ignition is going to close. The question is not whether, it is when and in how many places simultaneously. NASA's Fire Information System, which tracks active fire and thermal anomalies globally using satellite data, currently shows approximately 2,900 hotspots worldwide. That global context is worth noting for a moment. Fire is not absent from the planet. The American West is not a global outlier in terms of active burning, but the United States portion of that map, over the specifically affected states, is showing relatively low activity right now. And that contrast, a globally active fire environment surrounding a region primed for catastrophic ignition that has not yet ignited, is exactly the scenario that makes experienced incident commanders nervous. This is what I mean when I say Monday's not the beginning. Monday's the trigger. Everything that needed to happen before the trigger, the heat wave, the moisture extraction, the fuel preparation, the wind setup, the atmospheric alignment has already happened. The gun, to use an uncomfortable but accurate analogy, is already loaded. The conditions do not need to develop further. They are already there, waiting for the ordinary, unavoidable activities of human civilization and atmospheric physics to provide the spark. There is a specific kind of tension that comes from knowing that the worst-case scenario is fully assembled and simply waiting for an initiating event. It is different from watching a storm approach, because a storm at least announces itself. It is different from a flood, because flood risk is usually visible in the landscape. A pre-ignition environment looks calm. It looks, from the outside, like an ordinary late March day across parts of the American interior. The grasses look dry, but they usually look dry in late March. The wind is strong, but winds are often strong in March. The sky might be clear. And underneath all of that apparent normalcy, every single variable that determines fire behavior is pointed in the same direction at the same time. The most dangerous moment in this entire story is not when fires burn. It is right now, in the silence before them. Part 6. The snow that never existed. To understand how the American West arrived at this particular moment, with fuel at explosive moisture content and soils drained of the water reserves that should have carried them through spring, you have to go back to what did not happen this winter. Snow. There was supposed to be snow. There was supposed to be a great deal of snow, because snow is not simply precipitation in the West. Snow is the water storage system. The snowpack that builds in the mountains of Colorado, Utah, Wyoming, and the ranges beyond them is not incidental. It is the mechanism by which those regions receive their water supply for the spring and early summer. Snowpack accumulates slowly through the cold months, and then, as temperatures rise in spring, it releases that stored water gradually, feeding rivers, recharging groundwater, moistening soils, and delivering water to agricultural systems across multiple states. This is the system that the American West's entire ecological and hydrological calendar is built around. It is not a backup system, it is the system, and this winter it largely did not show up. Colorado and Utah are recording the lowest snowpack levels in the historical record. Not the lowest in a decade. Not the lowest since a particular bad stretch in the 1990s. The lowest ever measured. Snowwater equivalent readings, the standard metric for quantifying how much actual water is stored inside a snowpack, are showing more than 80% of monitoring stations sitting below normal across the region. January 2026 recorded the lowest snow cover extent in the continental United States since satellite-based snow monitoring began in 2001. That is a 25-year record, and it fell this past January, quietly, while most people were not paying attention to snowpack maps. That is not a bad snow year. That is a historically anomalous failure of a water storage system that an entire region's ecology depends on. And the failure was not random. The cause is not mysterious, which is almost more uncomfortable than if it were. The winter was warm, consistently, anomalously warm in a way that pushed the rain-snow line, the elevation above which precipitation falls as snow rather than rain, significantly higher than historical norms across most of the western mountain ranges. Precipitation that would normally accumulate as snowpack at middle elevations fell instead as rain. It hit the ground, ran into streams and rivers, and was gone within days. The mountains received moisture. They just did not keep it. This is where a concept that hydrologists call hydrological time shift becomes essential to understanding what we are looking at right now. The value of snowpack is not simply the water it contains. The value is the timing of when it releases that water. Snow is a storage and delivery mechanism with a built-in seasonal schedule. It accumulates during winter, when temperatures are cold and water demand from vegetation and agriculture is low. Then, as temperatures rise through spring, it melts gradually, releasing water into soils and river systems across a window of weeks and sometimes months. The release is slow, it is sustained. It carries moisture through the period when the land needs it most. The transition from cool spring into warm early summer, when vegetation is growing and fire conditions are beginning to build. When precipitation falls as rain instead of snow, that entire delivery mechanism disappears. Rain does not store. Rain does not wait for spring to schedule its release. Rain hits the ground and the clock starts immediately. The soil absorbs what it can in the first hours after the rain falls, and the rest becomes surface runoff moving toward lower elevations. Within days, the water that should have been sitting in the mountains, slowly preparing to sustain an entire region through spring and early summer, has already passed through the watershed and is heading toward the ocean. The winter precipitation happened. The water arrived. It just never stayed. What that means for March 2026 is striking in its clarity when you follow the chain. The West entered late winter and early spring, what should be the most hydrologically protected period of the year, when snowmelt would normally be actively moistening soils and keeping vegetation hydrated, with essentially no water reserves remaining in the system. The snowpack that should have been sitting in the mountains, slowly releasing moisture through March and April, was not there. The soils going into the heat wave were already running a moisture deficit. They were already below normal. They were already compromised before the heat wave added a single degree to the thermometer, and then the heat wave arrived, and it ran its extraction process on a system that had almost nothing left to give. Think about what that means physically. The drying engine we described, the persistent warmth pulling moisture out of soils and vegetation day after day, does not have to work very hard when the reservoir it is draining is already nearly empty. Normally, even a significant heat event takes weeks to draw soil moisture down to critical levels because there is a substantial water reserve in the system pushing back. Snowmelt is actively replenishing what the heat removes. The soils have a buffer. This winter, that buffer was essentially absent before the heatwave began. So when the temperatures climbed in early March, the extraction process moved faster, reached critical thresholds sooner, and produced fuel moisture conditions that would normally require months of summer heat to achieve. It achieved them in weeks, in March. The result is what the humidity sensors are measuring right now at 8%. The result is what the fuel moisture monitoring stations are recording across Wyoming, Colorado, Nebraska, and New Mexico. The result is the pre-ignition environment that has been assembled methodically, piece by piece, since November, through a warm autumn that never let soils recover from last summer, through a winter that delivered precipitation in the wrong form, through a heatwave that found the moisture reserves already exhausted and simply finished the job. Every step in that chain had a clear physical logic. None of it required unusual bad luck. It required only that a warming baseline climate do what a warming baseline climate does: push precipitation patterns, temperature distributions, and seasonal timing in directions that the infrastructure and ecology of the American West were not built to accommodate. This is not a story about an anomaly. This is a story about a system responding exactly as the physics predict it should respond under the conditions that have been accumulating for years. The snowpack failure was not a surprise to the hydrologists monitoring it. The fuel moisture collapse was not a surprise to the fire managers tracking it. What makes it a story is that all of these individually foreseeable developments arrived simultaneously, in the same place, in the same window of days, and produced a pre-ignition environment with no historical precedent for March. The uncomfortable question underneath all of this is not what happens this week. The uncomfortable question is what happens when this stops being an anomaly and becomes a sequence. What happens when winter fails not occasionally but regularly? When the warming baseline pushes the rain-snow line high enough, often enough, that snowpack-dependent water systems across the West can no longer count on the seasonal storage they were built around? What happens when spring never reliably gets its water, because winter stopped reliably delivering it in a form the land can hold? The answer to that question is not found in tomorrow's forecast. It is found in the trend lines, and the trend lines are not pointing in a reassuring direction. Part 7. Fuels the invisible crisis. If the snowpack failure is the upstream cause of where we find ourselves, the fuel situation is where that cause becomes physically dangerous in a way you can measure on the ground right now. Fuels, in fire management terminology, refers to the combustible material available in a given environment. Grasses, shrubs, dead plant material, accumulated organic debris, everything that can burn. And the National Interagency Fire Centre, the federal body that coordinates wildfire response at the national level, has issued assessments for this period that use language specifically noting fire behaviour not typically seen in March. That sentence is doing a great deal of work. What it means, translated out of institutional language, is that the fuel conditions they're observing belong to a different point in the fire season. They belong to July or August in a normal year. The calendar and the fuel moisture content are having a significant disagreement right now, and the fuel moisture content is winning. To understand how the fuels arrived at this state, you have to go back further than the heat wave. You have to go back to the wet years that preceded this period, because the climate does not move in a simple straight line. It oscillates. It delivers wet years and dry years in sequences that interact with each other in ways that are not always intuitive. The recent wet periods across portions of the western and central United States produced something that, at the time, looked unambiguously positive. Abundant rainfall and reasonable snowpack years drove significant vegetation growth. Grasses grew dense across the Great Plains, shrubs expanded across the intermountain zones. The biological productivity of the land when moisture is available is genuinely impressive. Plants grow fast, they grow thick, and they fill available space with an efficiency that reflects millions of years of evolutionary pressure to exploit good conditions while they last. But all of that biological productivity eventually dies. The grasses that grew thick in a good moisture year dry out and fall over. The shrub branches that expanded during a wet cycle accumulate dead wood as older growth gives way to newer. The organic material on the ground surface builds up. Layers of dead grass, shed leaves, fallen twigs, accumulated debris from multiple growing seasons. All of it becomes fuel. And this is the counterintuitive truth at the centre of fire science that tends to surprise people when they first encounter it. A good growing year does not protect a landscape from fire. A good growing year loads the landscape with the material that a subsequent bad year ignites. The wet cycle and the fire cycle are not opposites. They are sequential partners in a process that has been running across Western and Central North America for thousands of years. What has changed, and what makes the current situation qualitatively different from that historical pattern, is the speed at which the transition from wet and productive to dry and dangerous has occurred. The drying that normally takes a full summer season of heat and low humidity to achieve has happened in weeks. The fuel moisture content values being recorded right now belong to the back half of a normal fire season, not the beginning of one, and the fuel load available to burn, the accumulated product of those recent productive years, is sitting on the ground in quantities that fire managers are clearly treating as exceptional. The physics of fuel ignition are worth spending time on because they explain why the numbers being measured right now translate so directly into operational alarm. Dry fuel ignites faster than moist fuel. This is obvious enough, but the relationship is not linear, and the non-linearity is where the danger lives. As fuel moisture content drops from 20% toward 10%, ignition risk increases measurably, but remains within ranges that experienced fire managers can work with. Suppression resources can be positioned, fire lines can hold, helicopters and aircraft can make meaningful progress against an active fire front. Below 10%, the curve starts to bend sharply. Below 5 or 6%, you have crossed into a zone where the ignition physics change qualitatively. Fire does not just start more easily, it behaves differently once started. It moves differently. It interacts with terrain and wind differently. And the suppression calculus that works at higher moisture content stops working in ways that can catch even experienced crews off guard. Hot fuel ignites faster than cool fuel, which is why afternoon fire behaviour is almost always more extreme than morning fire behaviour. The same fuel, heated by hours of direct sun, becomes significantly more reactive. Fine fuel ignites faster than coarse fuel, which is why grass fires are so much more responsive to conditions than forest fires involving heavy timber. A grass fire does not need to heat a large fuel element to ignition temperature. It needs to heat a thin blade of dried vegetation that has essentially no thermal mass. The ignition is nearly instantaneous when conditions are right, and the spread from that ignition point is governed almost entirely by wind speed and the continuity of the fuel bed. Grass fires deserve considerably more attention than they typically receive in coverage of Western fire weather, because they are the primary threat across portions of the Great Plains and intermountain grasslands in the current setup. And they are dangerous in ways that are different from the forest fire danger most people have a mental model for. A forest fire in heavy timber is slow and hot. It builds intensity over time. It is difficult to stop once established, but it also moves at speeds that allow for some degree of response. A grass fire under high wind conditions moves at speeds that compress the response window almost to nothing. Fire spread rates in continuous grass fuels under 30 to 40 mph winds, and tomorrow we'll see gusts at 70, can reach multiple miles per hour. A fire that starts at the edge of a field can be at the far end of that field and into the next one before the first suppression resource has received the dispatch call. The wind interaction with grass fire is also qualitatively different from its interaction with forest fire. In a forest, terrain features, ridges, draws, changes in slope, can create opportunities for fire line construction because the fire's advance is somewhat constrained by the structure of the fuel. In a continuous grass fuel bed, the fuel is essentially homogeneous across the terrain. There are no natural fire breaks built into the landscape. A fire break that would hold against a forest fire can be overrun by a grass fire carried by wind, because the wind lifts burning material and carries it across the gap. The fire does not need to reach the fire break. It needs to get close enough for the wind to carry embers across it, and then it is already on the other side. Under 70 mph gusts, the distance that burning embers travel before landing makes traditional fire break widths essentially ineffective. What this means for the affected states right now is that the terrain is primed in a way that experienced fire managers recognize as genuinely alarming. The grasses across Wyoming, Nebraska, Colorado, and New Mexico are not behaving like late March grasses. They are behaving like late July grasses that have been through a full summer of heat. The fuel moisture content values being read from monitoring stations across these states are consistent with peak fire season conditions. The fuel loads are consistent with productive recent growing years. The wind forecast is consistent with extreme fire weather. All three of those things are true simultaneously in late March, in a region where the fire management infrastructure and seasonal preparation timelines are calibrated around fire season beginning roughly 3 months from now. And this is the part that I keep coming back to when I think about what the fuel situation actually means for tomorrow. The danger is invisible. You can drive across the affected states right now and see nothing that would register as alarming. The grasses along the highway margins look dry, but they often look dry in March. The fields look open and quiet. There is no visible sign of the crisis that fire managers are staring at on their monitoring screens. The fuel moisture content that is currently registering at levels consistent with peak fire season is not something you can see from a car window. You cannot look at a grass field and distinguish between fuel at 20% moisture and fuel at 4% moisture. They look identical. They look like grass. They look like March. They are not. They are loaded. They are waiting. And the only thing that separates the quiet scene visible from a highway right now from the kind of fire behaviour the National Interagency Fire Centre is describing in language it never uses in March is a spark. One spark in one location under tomorrow's wind field. The fuel does not need any further preparation. The landscape does not need conditions to develop further. Everything that needs to be in place is already in place. The invisible crisis of the fuel situation is precisely its invisibility. The fact that the most dangerous variable in tomorrow's fire weather equation is sitting in plain sight across hundreds of thousands of square miles of American terrain, completely undetectable to anyone who is not looking at the monitoring data. The fire managers are looking at the monitoring data. What they are seeing is what this story has been building towards since the first paragraph. Not a fire, something that is waiting, with extraordinary patience, to become one. Part 8. The jet stream broke the calendar. Something has been happening in the upper atmosphere over the past several months that helps explain why the pattern we're watching was able to develop and persist in the way that it has. And to understand it, we need to spend a moment with the jet stream. Not the full meteorological course, just enough to see why a disturbance in this atmospheric river has consequences that reach all the way down to 8% humidity in Wyoming. The jet stream is a band of fast-moving air in the upper atmosphere, typically moving at speeds of 100 miles per hour or more, that circles the northern hemisphere and acts as a steering mechanism for weather systems below it. The position and shape of the jet stream determines, to a significant degree, whether a given region receives storms or stays dry, whether cold air penetrates south or stays locked near the poles, whether weather patterns move through quickly or stagnate. It is the atmosphere's traffic manager, and like any traffic manager, when it starts making unusual decisions, the consequences ripple through every system that depends on it for orderly flow. To appreciate what the jet stream has been doing over the past several months, it helps to understand what it looks like when it is behaving normally. In its healthy configuration, the jet stream moves in a relatively tight, fast band across the upper atmosphere, completing its circuit of the northern hemisphere with moderate north-south swings. Weather systems embedded in this flow move through regions at a reasonable pace. Storms arrive, deliver precipitation, and move on, replaced by the next system in sequence. No single weather pattern dominates any given region for too long. The moisture and temperature conditions of a region get regularly refreshed by this procession of systems. Droughts can develop, but they develop slowly, because the jet stream eventually shifts and delivers the precipitation that interrupts them. This is the atmospheric rhythm that the seasonal calendars of every region in the northern hemisphere are calibrated around. It is the rhythm that determines when fire season starts, when the rains arrive, when snowpack accumulates. Everything downstream depends on the jet stream maintaining something close to that orderly flow. Earlier this year, that flow was disrupted by an event that most people have never heard of, and that deserves considerably more public attention than it receives. The atmosphere experienced what meteorologists call a sudden stratospheric warming event. The stratosphere is the layer of atmosphere sitting above the troposphere, above the weather, above the clouds, above the altitude where commercial aircraft cruise. It is cold, thin, and in normal conditions, relatively stable. A sudden stratospheric warming event is exactly what the name suggests: a rapid, dramatic increase in stratospheric temperatures over a very short period. We are talking about temperature rises of 30 or 40 degrees Celsius in just a few days. In a layer of atmosphere that normally changes slowly and predictably, that kind of thermal shock is extraordinary. The counterintuitive part, and this is where people sometimes get confused, is that warming in the stratosphere does not produce warming at the surface. It produces the opposite. The mechanism runs through the polar vortex, the large-scale circulation system in the upper atmosphere that normally acts as a containment barrier for cold Arctic air, keeping it penned near the poles during winter. The polar vortex is maintained by the temperature difference between the cold Arctic and the warmer mid-latitudes. When a sudden stratospheric warming event heats the stratosphere over the Arctic rapidly, it disrupts the temperature gradient that sustains the vortex. The vortex weakens, sometimes it splits, and when it weakens, its containment function degrades. Cold Arctic air that would normally stay near the poles begins to push southward into the mid-latitudes. But the polar vortex disruption is only the first consequence. The one that matters most for what we're examining today is what it does to the jet stream. When the polar vortex weakens, the jet stream loses the tight, organized structure that keeps it moving in a relatively straight band around the hemisphere. It becomes wavier. It develops larger amplitude ridges, northward bulges where the jet stream swings far toward the poles, and deeper troughs where it plunges southward. These ridges and troughs are larger in geographic scale and more persistent in time than the normal oscillations of a healthy jet stream, and a persistent ridge is, in atmospheric terms, a blocking event. The the western United States has been sitting under exactly such a ridge. A high-amplitude, persistent ridge in the jet stream over the western part of the continent creates what meteorologists call an omega block or a Rex block, depending on its specific configuration. The names are less important than the consequence, which is that the normal west-to-east progression of weather systems across the region essentially stops. Systems that would normally track through the area, delivering precipitation, moderating temperatures, and refreshing the atmospheric conditions over the region, get deflected. They go north of the block, or they go south of it, but they do not go through it. The block sits. Days pass. Weeks pass. The sun continues heating the region beneath the ridge. The dry air continues pulling moisture from soils and vegetation. The drying engine continues running because the atmospheric configuration that would normally interrupt it, a passing storm system, a period of cloud cover, a significant precipitation event, cannot get through. This is the mechanism behind the persistence that transformed the March 2026 heatwave from a record-breaking temperature event into a multi-week drying process. It was not simply that temperatures got high. Temperatures get high during heat waves with some regularity. What was different about this event was the duration and the completeness of the moisture extraction it was able to achieve, and that duration was a direct product of the blocking pattern that kept the drying conditions locked in place over the region. Without the atmospheric block, the heatwave peaks and the next weather system eventually pushes through. With the atmospheric block, the heatwave peaks and then simply continues in a diminished but still drying form day after day until the moisture reserves are gone. The sudden stratospheric warming event that initiated this chain is itself a subject of increasing scientific attention in the context of a changing climate. The polar vortex has always experienced disruptions. They are not new phenomena, but researchers examining the historical record alongside climate model projections are finding patterns worth taking seriously. As the Arctic warms faster than the rest of the planet, a phenomenon called Arctic amplification, which is one of the most robust signals in the observed climate record, the temperature gradient between the Arctic and the mid-latitudes decreases. The polar vortex is sustained by that gradient. A smaller gradient means a less stable vortex, one that is more susceptible to the kind of disruption that a sudden stratospheric warming event can trigger. The math is not complicated, even if the atmospheric dynamics are. A warming Arctic reduces the structural integrity of the system that contains cold air near the poles and keeps the jet stream organised. A less organised jet stream develops more extreme, more persistent ridges and troughs. More persistent ridges produce more extended blocking events. More extended blocking events produce more situations like the one that assembled the pre-ignition environment, now sitting across 9 western states. This is a feedback chain that connects Arctic sea ice loss, something that happens thousands of miles from Wyoming, to fire weather conditions in Wyoming. It connects upper atmosphere physics to the 8% humidity reading that fire managers are staring at on their screens right now. It connects a stratospheric temperature spike in January to the fuel moisture content values being recorded across Colorado and Nebraska in late March. The atmospheric system is connected across scales that human intuition is not naturally built to track. The sudden stratospheric warming event felt at the time like an abstract meteorological curiosity. What it left behind is anything but abstract. And this is where the hypothesis that emerges from all of this becomes genuinely uncomfortable to sit with. The question is not simply whether the jet stream disruption that produced this particular blocking event was unusual. The question is whether the frequency and persistence of these disruptions is changing in a directional way. Whether the jet stream is becoming structurally less stable over time as the conditions that sustain its organised flow degrade. If the answer to that question is yes, even partially yes, then the implication extends well beyond this fire season. It reaches into the fundamental assumptions embedded in every seasonal calendar, every agricultural planning system, every fire management preparedness timeline, every water resource management framework across the Northern Hemisphere. Those systems were all built around a jet stream that behaved with some degree of seasonal regularity. They were built around the assumption that midsummer fire conditions arrive in midsummer, that winter precipitation falls as snow at the elevations where snowpack forms, that spring moisture arrives on a schedule that the landscape can use. If the jet stream is becoming decoupled from the seasonal calendar, if it can deliver midsummer fire conditions in March as readily as it delivers them in August, because the atmospheric blocks that produce those conditions are no longer constrained by seasonal patterns, then those planning frameworks are calibrated to a version of the atmosphere that may no longer reliably exist. What if seasons are no longer tied to time, but to unstable atmospheric patterns that can assemble anywhere on the calendar, hold in place for weeks, and leave behind conditions that belong to a completely different time of year? That is not a rhetorical question. It is the question that the data from the past several months is asking. And the answer, whatever it turns out to be, will matter far beyond the fire season that is beginning, in late March, 3 months ahead of schedule. Part 9. La Niña's Ghost and El Niño's Arrival. The ocean is having a conversation with the atmosphere, and right now the message it is sending is ambiguous in a way that makes forecasting more uncertain than it would otherwise be. To understand why that ambiguity matters for what is happening across the American West right now, it helps to understand the basic mechanics of the climate system that governs precipitation patterns across the United States more than any other single factor. The El Niño Southern Oscillation, ENSO in the shorthand that climate scientists use, is a recurring pattern of ocean temperature variation in the tropical Pacific that has outsized influence on weather patterns across much of the globe. It is not a storm. It is not an event in the conventional sense. It is a slow oscillation in the temperature of a large section of the Pacific Ocean, cycling between warmer than average conditions called El Niño and cooler than average conditions called La Niña, with neutral periods in between. And the position of that oscillation at any given time has consequences that reach across hemispheres and reshape seasonal weather patterns in ways that forecasters have spent decades learning to anticipate. The Oceanic Niño Index, which measures sea surface temperature anomalies in the central Pacific and is the standard metric for tracking where the ENSO cycle stands, is currently sitting near neutral. But near neutral is not the same as stable, and that distinction is doing significant work in the current situation. The system is in transition, and transitions in the ENSO cycle are the periods of greatest forecasting uncertainty, the moments when the ocean is moving between states and the atmospheric patterns that each state produces are overlapping, interfering, and producing combinations that do not fit the templates cleanly. La Niña conditions, cooler than average sea surface temperatures in the central and eastern tropical Pacific, persisted through much of the recent period leading into this year. La Niña is not an obscure academic phenomenon. Its effects on United States weather are well documented and significant. When the central Pacific cools, it shifts the atmospheric circulation patterns that govern where storm tracks develop and where they go. The jet stream, which we examined in detail in the previous section, tends to be pushed northward during La Niña. This northward displacement has a direct consequence for the southern tier of the United States. Storm systems that would otherwise track through the southwest and deliver precipitation to California, Arizona, New Mexico, and the broader southern plains get steered away. The southern routes close, precipitation drops, drought conditions develop and deepen over months of reduced moisture input. This is precisely the pattern that played out across the American West and Southwest during the La Niña period. The jet stream sat high. The storm tracks bypassed the southern and central parts of the country. The soil moisture deficit that the region entered this fire season carrying was, in significant part, a product of months of La Niña-influenced precipitation reduction. The drought did not arrive suddenly. It built slowly, quietly, through a series of storm systems that tracked north of where they were needed, through a series of months where the precipitation totals fell below normal in ways that individually seemed manageable, but collectively produced a moisture debt that the region is now carrying into fire season. That La Niña signal is now fading. The sea surface temperatures in the central Pacific are warming back toward neutral. The Oceanic Niño Index is moving. And here is where the distinction between the ocean state changing and the atmospheric consequences of that change reversing becomes critically important. When La Niña ends, the drought it helped produce does not end simultaneously. The ocean can shift its temperature on a timescale of months. The soil moisture deficit, the vegetation moisture deficit, the accumulated dryness of the landscape, these respond on different timescales entirely. The land carries the moisture debt that La Niña ran up even after the ocean has moved on. The debt does not clear when the creditor changes. The American West is right now in exactly that position. The La Niña that helped create the drought conditions underpinning this fire weather event is technically fading. but the drought it produced is fully present, fully active, and fully contributing to the 8% humidity and explosive fuel conditions that tomorrow's forecast is built on. The direction the ocean appears to be moving next adds another layer of complexity to an already complicated picture. Ocean heat content in the central and eastern tropical Pacific has been building. Forecasters are discussing the development of El Niño conditions in the latter part of 2026. El Niño produces a broadly different set of atmospheric consequences than La Niña: wetter conditions across the southern United States in winter, drier conditions in the Pacific Northwest, a jet stream that tends to take a more southerly track and deliver storm systems to regions that La Niña had been bypassing. In a simple, sequential world, you would expect the transition from La Niña to El Niño to eventually bring relief to the drought-stressed regions of the American West. More precipitation, lower fire risk, recovery of soil and vegetation moisture content. But the transition period is not simple, and the world the atmosphere is operating in right now is not the world those templates were built to describe. The gap between when La Niña ends and when El Niño fully establishes itself can span many months, and during that gap the atmospheric patterns that each state produces do not cleanly hand off from one to the other. They overlap, they interfere. The atmospheric system receives conflicting signals from an ocean that is neither clearly in one phase nor clearly in another, and the resulting weather patterns can be erratic, poorly predicted by the standard ENSO templates, and inconsistent with what either a pure La Niña or a pure El Niño forecast would suggest. Layer on top of that the factor that makes this particular transition period different from historical transitions, and the uncertainty compounds further. Global sea surface temperatures across the world's oceans, not just the tropical Pacific but the Atlantic, the Indian Ocean, the waters surrounding every continent, have been running at or near record levels for an extended period. The global ocean is warmer than it has been at any point in the instrumental record. This baseline warming is not part of the ENSO cycle. It is not La Niña. It is not El Niño. It is a separate forcing factor that sits underneath the ENSO oscillation and modifies its effects. A warmer global ocean delivers more energy to the atmospheric system regardless of which phase of ENSO is active. It intensifies the atmospheric dynamics associated with whatever pattern the ENSO cycle is producing. It raises the ceiling on how extreme the anomalies generated by those patterns can become. What this means in practice is that the forecasting frameworks built around historical ENSO relationships, the templates that tell meteorologists and climate scientists what La Niña typically does to precipitation in the southwest, what El Niño typically does to storm tracks across the south, how the transition between phases typically plays out, are being applied to an atmospheric system that is operating at a higher energy level than those templates were calibrated against. The relationships may still hold directionally. La Niña still tends to reduce southern precipitation. El Niño still tends to increase it. But the magnitude of the anomalies those patterns produce, and the behaviour of the system during the transition between them, may not fit the historical templates as reliably as they once did. The models know this. The scientists building and running those models know this. And the acknowledgement of that uncertainty, coming from the people whose professional expertise is built around these forecasting systems, is itself worth registering. There is something specific about the current moment that deserves to be stated plainly. The American West right now is caught in an overlap zone, carrying the moisture debt of a La Niña that is ending, facing a transition period toward an El Niño that has not yet arrived, sitting under an atmosphere energized by global ocean temperatures running at record levels, and experiencing atmospheric blocking driven by jet stream disruptions that the ENSO cycle alone does not fully explain. These are not independent factors that can be analysed separately and added together. They are interacting factors whose combined behaviour is genuinely difficult to predict with the precision that operational forecasting requires. The uncertainty is not a failure of the science. It is an honest description of a system whose component parts are doing multiple things simultaneously. This is the atmospheric context in which tomorrow's fire weather event is occurring. Not a simple, well-understood pattern playing out according to a familiar template. A complex, multi-factor convergence of signals from a Pacific Ocean in transition, a global ocean at record temperatures, a jet stream disrupted by stratospheric events connected to Arctic warming, and a landscape carrying drought conditions assembled over months of La Niña-influenced precipitation reduction. Each of those factors contributed something to the pre-ignition environment now sitting across 9 western states. None of them individually tells the complete story. Are we entering a phase where climate patterns overlap rather than cycle cleanly? The honest answer, the one that the data and the scientists examining it are both pointing toward, is that we may already be in it. The forecasting models are not certain. The atmospheric scientists are not certain. And when the people who built the systems designed to anticipate these patterns start publicly acknowledging the limits of what those systems can reliably predict under current conditions, that acknowledgement is itself a signal, not of failure, of a climate system that is operating in territory the historical record does not fully cover, and doing so in ways that are showing up right now in the fire weather forecast for tomorrow morning across 9 western states. Part 10. The power grid knows what's coming. There is a behaviour that infrastructure managers engage in when the risk models are showing them something they take very seriously, and it is worth paying attention to because infrastructure managers are, by training and institutional incentive, conservative. They do not act preemptively without cause. They do not shut down systems or impose restrictions based on speculation. They act on data, and right now the data is producing actions that tell a story of their own. Wyoming utilities are implementing precautionary power shutoffs in response to the forecast fire weather conditions for tomorrow. The power is being cut before anything has happened, before a single fire has started, before a single power line has failed, before any of the conditions that would normally trigger an emergency response have materialized. The shutoffs are happening in anticipation of conditions that, as of this moment, exist only in forecast models and monitoring data. And that sequence, action preceding event, infrastructure responding to prediction rather than reality, is worth examining carefully, because it tells you something important about what the people responsible for managing these systems actually believe is coming. To appreciate the significance of what Wyoming utilities are doing, it helps to understand what a precautionary power shutoff actually costs. The economics are not trivial. When a utility implements a public safety power shutoff, the direct costs include the operational expense of de-energizing and re-energizing transmission and distribution infrastructure across potentially large geographic areas, the deployment of field crews to physically manage switching equipment, the coordination with emergency services and public agencies that depend on reliable power for their own operations, and the customer service burden of managing thousands of affected accounts simultaneously. The indirect costs are larger. Businesses lose revenue, residents lose refrigeration, heating, medical equipment function, and the basic infrastructure of daily life. Agricultural operations that depend on electrically powered irrigation or climate control face losses that can be significant. Cold storage facilities, water treatment plants, and communications infrastructure all operate on electricity. A shutoff is not a minor inconvenience distributed across a population. It is a substantial economic and operational disruption that utilities absorb real reputational damage for implementing, even when they implement it correctly. And yet the assessment of fire risk tomorrow is apparently sufficient to justify absorbing all of those costs. That tells you something, not about the utilities being alarmist, about the fire risk being genuinely alarming. Until relatively recently, precautionary power shutoffs of this type were almost exclusively a California practice, and they became a California practice through a specific and painful history. The catastrophic wildfires of the latter part of the last decade, fires that destroyed entire communities, killed dozens of people, and produced liability judgments that pushed at least one major California utility into bankruptcy, were linked in significant part to failures of electrical infrastructure under extreme fire weather conditions. Power lines contacting vegetation, equipment arcing under high wind stress, transmission infrastructure failing in ways that dropped fire directly into critically dry fuel. The legal and financial consequences of those events were severe enough to force a fundamental rethinking of how California utilities manage fire risk. The precautionary shutoff became a standard tool not because utility executives wanted to implement it, they did not, and many resisted it initially, but because the alternative, maintaining energized infrastructure through extreme fire weather and accepting the liability consequences of any ignition that resulted, became financially untenable. The regulatory environment changed alongside the legal environment. California established frameworks that provided liability protection for utilities that implemented shutoffs according to defined protocols, which shifted the cost-benefit calculation significantly. Before those frameworks existed, a utility faced costs on both sides of the decision. costs from shutting down, and potential costs from not shutting down. After the frameworks existed, the calculus simplified. The cost of a shutoff is large but bounded and manageable. The cost of a utility-caused catastrophic fire in the current legal environment is potentially existential for the company. The spread of this practice to Wyoming is not simply a policy trend moving across state lines. It represents a geographical expansion of the recognition that the fire risk conditions once considered specific to California's particular combination of terrain, climate, vegetation, and infrastructure are now appearing in states that did not historically manage their infrastructure against that risk profile. Wyoming is not California. Its terrain is different. Its vegetation types are different. Its infrastructure architecture is different. Its historical relationship with wildfire is different. And yet Wyoming utilities are now making the same calculation that California utilities were forced into by catastrophic experience. That the conditions forecast for tomorrow are dangerous enough that energized power infrastructure represents an unacceptable ignition risk. That geographical expansion is a signal, not a subtle one. When the risk management practices developed in response to California's specific fire history start appearing in Wyoming in late March, it means the fire risk conditions that drove those practices in California are now present in Wyoming in late March. The practice follows the risk, and the risk has moved. The legal evolution happening around utility liability for fire ignition deserves attention in its own right, because it reflects a broader shift in how the legal system is processing the relationship between infrastructure management decisions and climate-driven fire risk. Courts and legislatures across fire-affected states have been working through questions that did not have clear answers in previous legal frameworks. When a power line starts a fire under conditions that were forecast to be extreme, and the utility chose to maintain energized infrastructure through those conditions, what is the appropriate allocation of liability? When a utility implements a shutoff that causes economic harm to affected customers and businesses, and no fire occurs, was the shutoff justified? These questions are being answered slowly and unevenly through litigation, legislation, and regulatory proceedings across multiple states simultaneously. The direction of those answers is generally moving toward greater legal protection for utilities that implement precautionary shutoffs according to defined protocols, and greater liability exposure for utilities that fail to take precautionary action under conditions that were clearly foreseeable as dangerous. That legal direction is itself a form of institutional acknowledgement that the fire risk associated with energized infrastructure under extreme fire weather conditions is real, foreseeable, and manageable through precautionary action. The law is, in its characteristically slow way, catching up to the physics. What makes the Wyoming situation particularly worth examining is the timing. Precautionary shutoffs in California typically occur during the peak of fire season, late summer and fall, when the combination of dry vegetation, low humidity, and offshore wind events called Diablo or Santa Ana winds creates the conditions for extreme fire behavior. Those shutoffs happen in a seasonal context where extreme fire weather is expected, and the infrastructure management protocols have been calibrated around it. What is happening in Wyoming is happening in late March, in a seasonal context where extreme fire weather was not, until very recently, part of the operational planning framework. The shutoffs are not just geographically expanding, they are temporally expanding, moving earlier in the calendar year in ways that reflect the same displacement of fire season conditions we have been tracking throughout this story. And here is the part that I keep returning to when I think about what the utility response to tomorrow actually means. The utilities are not reacting to a fire. They are acting on a model output, a forecast, an assessment of atmospheric conditions that have not yet produced the catastrophic event they are trying to prevent. They are treating the pre-ignition environment, the same pre-ignition environment we have spent this entire story examining, as a real and actionable threat rather than a speculative future possibility. The infrastructure system has processed the same data that the fire managers and the meteorologists and the climate scientists are looking at, run it through its own risk frameworks, and arrived at a conclusion. The conditions forecast for tomorrow are dangerous enough that we will accept certain immediate significant costs in order to reduce the probability of uncertain, future, potentially catastrophic costs. That is not overreaction. That is exactly what rational risk management looks like when the downside scenarios are severe enough. It is the same logic that leads airlines to ground flights when weather models show conditions below safety thresholds, not because a crash has occurred, but because the probability of a crash under those conditions exceeds the acceptable threshold. The system acts on the forecast because the forecast is describing a risk environment that the system was designed to respond to. But rational risk management operating correctly still leaves a question open that I think is worth sitting with honestly. The utilities are making shut-off decisions based on model outputs and forecast data. They are seeing something in those outputs that is producing significant preemptive action. The question of what specifically those models are showing, what the full risk assessment looks like when you have access to the complete data picture that utility risk managers and fire weather forecasters are working from, is not fully public. The red flag warnings are public. The critical fire weather risk designation is public. The forecast humidity and wind values are public. But the internal risk assessments, the specific infrastructure vulnerability analyses, the modelling of how particular ignition scenarios would propagate under tomorrow's conditions across specific terrain and fuel configurations, that analysis exists, and it is informing decisions that affect millions of people, and it is not fully visible. When systems start acting before disasters happen, when utilities shut down proactively and federal agencies issue language in March that they have never issued in March, what they are seeing is a risk picture that the public summary statistics do not completely capture. The 8% humidity is visible. The 70-mile-per-hour gusts are visible. What is less visible is the integration of all of those factors with specific infrastructure vulnerability, specific fuel distribution, specific terrain configuration, and specific modelling of how a fire starting at any of dozens of potential ignition points would behave under tomorrow's conditions. That integrated picture is what is driving the decisions, and the decisions, in their conservatism and their cost and their geographic and temporal expansion, suggest that the integrated picture is considerably more alarming than the public summary suggests. What exactly are they seeing, and what precisely are they choosing not to say out loud? Part 11. AI is now predicting wildfires before ignition. The practice of predicting where fires will start before they start is no longer theoretical. It is operational, or at least approaching operational status, at several agencies and research institutions, and the tools being used represent a significant departure from how wildfire risk has traditionally been assessed. And to understand why that matters for tomorrow specifically, for the pre-ignition environment sitting across 9 Western states right now, you have to understand what the traditional approach gets right, and more importantly, what it fundamentally cannot do. The traditional approach to fire weather forecasting is atmospheric in its foundation. Meteorologists model the conditions: temperature, humidity, wind speed and direction, atmospheric stability, and identify areas where those conditions exceed the thresholds associated with elevated fire danger. This is what produces red flag warnings. This is what generates the critical fire weather risk designation from the Storm Prediction Center. It is genuinely useful. It is scientifically rigorous. It tells emergency managers and fire agencies where the dangerous conditions exist across the landscape, so they can pre-position resources, issue public warnings, and prepare suppression infrastructure for likely demand. In a system with limited resources and enormous geographic area to cover, knowing where conditions are dangerous is essential. But here is what a red flag warning cannot tell you. It cannot tell you where, within the dangerous area, the first ignition is most likely to occur. It cannot tell you which specific stretch of highway, which specific transmission corridor, which specific terrain feature represents the highest probability ignition point given tomorrow's wind field and the spatial distribution of fuel conditions. It cannot tell you, given an ignition at a specific location, how fast the fire will spread in the first 30 minutes, which direction it will move as the wind field shifts through the afternoon, where the spot fires generated by that initial ignition are most likely to land and establish. And it cannot tell you which communities, given all of those factors, are in the highest probability impact zone. A regional danger designation tells you the conditions are dangerous. It does not tell you where the danger is going to materialize or what it is going to do when it does. Machine learning systems trained on historical fire data are beginning to address precisely those questions in ways that conventional meteorological modeling was never designed to handle. The architecture of these systems is fundamentally different from atmospheric modeling. Where a weather model starts with physics, with equations describing fluid dynamics, thermodynamics, and radiative transfer, and generates forecasts by solving those equations forward in time, a machine learning fire prediction system starts with data. Enormous quantities of historical data, every recorded fire ignition point correlated with the conditions present at that location at the time of ignition. Every documented fire spread trajectory matched against the terrain, fuel and wind conditions that governed it. Every instance of spot fire behaviour mapped against the distance and direction of ember transport under observed wind conditions. The inputs to the most developed of these systems go considerably beyond weather conditions. They incorporate fuel moisture data from the network of ground-based monitoring stations distributed across the landscape, supplemented by satellite-derived fuel moisture indices that can estimate conditions in areas between stations. They incorporate terrain analysis, slope, aspect, topographic position, the drainage features and ridge lines that channel wind and influence fire behaviour. They incorporate historical ignition point data correlated with infrastructure location and human activity patterns, because fire ignitions are not random. They cluster around roads, power lines, recreational areas, and agricultural operations in ways that reflect the spatial distribution of ignition sources. They incorporate real-time satellite thermal anomaly detection, which can identify heat signatures consistent with ignition before a fire is large enough to be reported through conventional channels. And they incorporate population and road network data, because the operational consequence of a fire depends not just on where it starts and how it spreads, but on what is in its path and how accessible the affected area is to suppression resources. The output of these systems, in their most developed implementations, is not a regional danger zone painted in red across a map. It is a probabilistic map of ignition likelihood at fine spatial resolution, individual grid cells of perhaps 100 meters or less, updated continuously as weather conditions evolve in real time. For tomorrow's forecast, a fully operational version of such a system would not be showing emergency managers a large red zone across Wyoming, Colorado, and Nebraska. It would be showing them a ranked list of specific locations. The particular stretch of Interstate 25 where vehicle-caused ignitions have historically concentrated under high wind conditions. The specific transmission corridor where aging infrastructure under wind stress creates spark risk. The terrain feature northeast of a particular community where the combination of slope, aspect, and wind direction means that spot fires from an initial ignition would most likely establish secondary burn zones. That is operationally useful information in a way that a regional danger designation is not, because it allows resource pre-positioning at specific locations rather than general readiness across a large area, and it allows evacuation planning to begin before ignition rather than after. Several federal and state agencies are actively experimenting with these systems, and some have moved beyond experimentation into limited operational deployment. The United States Forest Service has been developing and testing fire spread prediction tools that incorporate machine learning components. State fire agencies in California, Oregon, and Colorado have been piloting ignition prediction systems that use the kind of multi-factor data integration described above. The National Oceanic and Atmospheric Administration has been investing in improved integration between weather modelling and fire behaviour modelling. The direction of travel across the federal and state fire management infrastructure is clearly toward greater use of these tools, even if the current state of deployment is uneven, and the integration into official incident command decision-making remains incomplete. The incompleteness is not primarily a technical problem. The algorithms work, the data pipelines exist. The computational infrastructure to run these systems in real time is available. The challenge is institutional, and institutional challenges are often harder to solve than technical ones. Wildfire response systems have organizational cultures built around frameworks that have been developed and refined over decades. The Incident Command System, the National Interagency Coordination Center, the dispatch and resource allocation protocols that govern how suppression resources move across the country in response to fire activity. These frameworks are built around the outputs of traditional fire weather forecasting. They are calibrated around red flag warnings and fire weather watches and danger ratings. Incorporating probabilistic machine learning outputs into operational decisions within these frameworks requires not just the tools but the training, the institutional trust, and the procedural adaptation to use them appropriately. There are also genuine concerns about false positives that deserve honest acknowledgement. A fire prediction system that tells an incident commander there is a 70% probability of ignition at a specific location within the next 6 hours is making a probabilistic statement, not a certainty. 30% of the time, that prediction is wrong. If emergency managers begin evacuating communities based on high probability predictions that subsequently do not materialize, the erosion of public trust in warnings can have real consequences for future evacuations that are genuinely necessary. The boy who cried wolf problem is not hypothetical in emergency management. It is documented and it is serious. Designing systems that communicate probabilistic predictions accurately in ways that support good decision-making without generating prediction fatigue is a problem that the people building these tools are actively working on and have not fully solved. But the direction of travel is clear enough that the question of what happens when we can predict disasters before they exist has moved from philosophical to practical. It is no longer asking what it would mean to have this capability. It is asking how to use a capability that is arriving, unevenly, imperfectly, but genuinely, in operational fire management right now. The decisions being made today about how to communicate probabilistic ignition predictions, about what probability threshold triggers what operational response, about who receives what level of detail and through what channels, are design decisions with real consequences for how tomorrow's conditions play out across the affected states. And while those systems are running their predictions and the operational frameworks are absorbing their outputs, the oceans are providing the global context that explains why we keep arriving at moments like this one with increasing frequency. Global average sea surface temperatures have been running at or near record levels for an extended period, with readings pushing above 21 degrees Celsius on a globally averaged basis, a threshold that would have been considered extraordinary at any previous point in the instrumental record. The oceans cover roughly 70% of the planet's surface and absorb a disproportionate share of the energy that accumulates in the climate system from enhanced greenhouse forcing. When that absorbed energy raises ocean temperatures to the levels observed over the past 2 years, the oceans are not simply warm in the way that a warm summer makes a swimming pool comfortable. They are operating as energy reservoirs at a capacity that has no historical precedent in recorded measurement, storing and redistributing heat in quantities that modify the atmospheric circulation patterns governing weather across every continent. That stored energy transfers continuously into the atmosphere, through evaporation, which carries latent heat upward into the atmospheric column, through direct sensible heat exchange at the ocean surface, which warms the lowest layers of the atmosphere above the ocean, through the modification of temperature gradients between ocean regions that drive the large-scale circulation patterns, the trade winds, the subtropical jets, the blocking ridges that determine where storms go and where they do not. A warmer ocean does not produce warmer weather in a simple, direct, localized sense. It produces a more energetic atmospheric system, one capable of generating more intense anomalies, sustaining blocking patterns for longer, and pushing heat events to magnitudes that would have been statistically nearly impossible in a cooler baseline climate. The connection between record ocean temperatures and the fire weather event unfolding across the American West tomorrow operates at 2 distinct levels, and both matter. At the immediate level, the anomalously warm Pacific has been modifying the atmospheric circulation patterns over the western United States throughout the period that assembled the pre-ignition environment, contributing energy to the blocking ridge that locked heat over the region, reducing the temperature gradient that would normally drive storm systems through the area, maintaining the atmospheric configuration that kept the drying engine running week after week. At the longer-term structural level, the elevated baseline of ocean energy means that the atmospheric system responsible for generating tomorrow's conditions is operating with more available energy for producing extremes than it was a generation ago. The ceiling on how intense heat events can become, how persistent blocking patterns can be, how completely moisture can be extracted from a regional landscape, all of those ceilings have been raised by ocean temperatures running at record levels. There is something that should stop you for a moment when you follow this chain all the way through. The fires that may start tomorrow will burn grass and shrubs along highway margins and in open fields across Wyoming, Nebraska, and Colorado. The smoke will be visible from 100 miles away. Cameras will capture the flames. Investigators will eventually identify the specific ignition source, a power line, a vehicle, a lightning strike. That ignition source will feel like the cause, it will be the proximate cause, but the fuel that ignition touches will be dry, because of a heat wave that persisted, because of a blocking pattern that was energized by an ocean, running at temperatures with no historical precedent. The origin of tomorrow is not on land at all. It is sitting in the Pacific and in the Atlantic and in every body of ocean water that has been absorbing the accumulated energy of a warming climate system and releasing it continuously into the atmosphere that governs everything above it. The real engine of this event has been running for years. Tomorrow is just when you can finally see the exhaust. Part 13. The rise of flash droughts. There is a type of drought that the traditional monitoring frameworks were not designed to catch in time, and it is becoming more common in ways that are directly relevant to what produced the conditions we're examining for tomorrow. To understand why it matters so much for this specific story, you first have to understand what drought monitoring was built to do, and the assumptions embedded in that design that flash drought systematically violates. The United States Drought Monitor, the standard framework through which drought conditions are tracked, classified, and communicated to the public and to decision makers, was designed around a conception of drought as a slow-moving phenomenon. Traditional drought develops over months, sometimes years. It is the product of a sustained precipitation deficit, season after season of below normal rainfall or snowfall, gradually drawing down the moisture reserves stored in soils, groundwater, and vegetation. This slow accumulation of deficit is what gives traditional drought monitoring frameworks their characteristic timescales. The Drought Monitor updates weekly. Its classifications reflect conditions assessed over periods of weeks to months. Its inputs include long-term precipitation anomalies, stream flow records, groundwater levels, and soil moisture indices that capture the integrated effect of conditions over extended periods. This design made sense when drought was understood as a slow process, because a slow process can be tracked on weekly timescales without missing critical transitions. The monitoring framework and the phenomenon it was designed to track were matched in their temporal characteristics. Flash drought operates on a fundamentally different timescale, and that mismatch between the phenomenon and the monitoring framework is where the danger lives. A flash drought is defined not by its severity at peak, but by the speed at which it develops. Where traditional drought takes months to move from near-normal conditions to severe moisture deficit, flash drought can complete that same transition in 2 weeks, sometimes less. The conditions that appear essentially normal on a Monday morning can, by the following Monday, have produced soil moisture deficits and vegetation moisture content values consistent with months of traditional drought accumulation. The weekly update cycle of the Drought Monitor is not fast enough to capture that transition in real time. By the time a flash drought appears in the official classifications, the transformation of the landscape is already complete. The monitoring system is documenting history, not warning of an emerging threat. The trigger for flash drought is not primarily a lack of precipitation, though reduced precipitation contributes. The primary driver is intense evapotranspiration, the combined process by which heat drives moisture out of soils directly through evaporation and out of vegetation through transpiration. And the atmospheric variables that maximize evapotranspiration rates are precisely the variables that have been present across the American West throughout the period following the March 2026 heatwave. High temperatures accelerate evaporation from soil surfaces by increasing the energy available to convert liquid water to vapor. Low humidity creates a steep gradient between the moisture content of the soil and vegetation and the moisture content of the surrounding air, accelerating the rate at which moisture moves from the land surface into the atmosphere. Wind continuously replaces the air immediately above the soil and vegetation surface with drier air from above, preventing the local humidity from rising to levels that would slow the evaporation rate. Heat, low humidity, and wind are the three-part engine of flash drought onset. They are also, not coincidentally, the three defining characteristics of the fire weather conditions we have been examining throughout this story. Flash drought and extreme fire weather are not separate phenomena that happen to co-occur. They are products of the same atmospheric configuration, running simultaneously, reinforcing each other. The southern and central plains portions of the states under fire weather watches right now have experienced conditions consistent with flash drought onset throughout the period since the heatwave began. Soil moisture monitoring stations across the region have recorded declines that, in their speed and magnitude, belong to the flash drought category rather than the traditional drought category. The rate of moisture loss from soils across Colorado, Wyoming, Nebraska, and New Mexico over the past several weeks has been consistent with evapotranspiration rates that occur during peak summer heat, not late winter transitioning to spring. The atmospheric conditions have been extracting moisture from the landscape at a pace that the traditional drought monitoring system, operating on its weekly update cycle and its monthly to seasonal input timescales, was not designed to track in real time. What this means practically is that the warning system most Americans rely on to understand regional drought conditions was not showing the full picture of what was happening to the landscape during the weeks that assembled the pre-ignition environment. The drought monitor classifications for the affected region during this period have been serious, reflecting the accumulated deficit from the La Niña period and the snowpack failure we discussed earlier. But the flash drought component, the rapid, intense additional extraction of moisture from soils and vegetation, driven by the heat wave and its aftermath, may have moved faster than the weekly classification cycle could fully capture. The monitoring system and the phenomenon have been operating at different speeds, and the phenomenon has been winning. This has a direct and immediate consequence for fire risk assessment that is worth stating plainly. Fire weather forecasting uses fuel moisture content as one of its primary inputs. The fuel moisture values being fed into fire behaviour models are derived from a combination of direct measurements at monitoring stations and modelled estimates based on weather conditions. If the flash drought process has driven fuel moisture content to values more extreme than the monitoring network's spatial coverage can fully capture, if there are areas between stations where the drying has been more severe than the interpolated estimates suggest, then the fire behaviour models may be working with fuel moisture inputs that are, in some locations, less alarming than the actual ground conditions. The models are showing something very dangerous. The reality on the ground may in places be worse than what the models are showing. The geographic expansion of flash drought beyond its historically recognised zones is a trend that researchers have been documenting with increasing concern over the past decade. Flash droughts have been recorded across sub-Saharan Africa, where rapid moisture loss has devastated agricultural systems in regions that historically experienced gradual seasonal drying. They have been documented across the interior of South America, including in portions of Brazil and Argentina, where flash drought onset has preceded major fire seasons that caught regional authorities unprepared. They have appeared across parts of Central and Eastern Europe, including regions with historically stable growing season moisture that had no institutional framework for managing rapid drought onset, because rapid drought onset was not part of their historical experience. The phenomenon is not expanding slowly. It is expanding in pace with the atmospheric conditions that produce it, which means it is expanding in pace with the warming of the climate system that makes those conditions more frequent and more intense. The research literature on flash drought has been growing rapidly over the past several years, driven by the recognition that traditional drought science, built around the slow-moving precipitation deficit model, was missing an increasingly important category of drought event. Scientists have been developing improved detection methods, faster updating soil moisture products derived from satellite measurements, and early warning indices designed to identify the atmospheric precursors of flash drought onset before the moisture deficit becomes severe. Some of these tools are now operational in limited contexts. The National Oceanic and Atmospheric Administration has been working on flash drought early warning capabilities. Several agricultural agencies have developed rapid response soil moisture monitoring products specifically designed to catch flash drought onset in near real time. The monitoring infrastructure is improving, but it is improving in response to a phenomenon that is itself accelerating, and the gap between the speed of flash drought development and the speed of the monitoring systems designed to catch it has not yet closed. For fire season preparation specifically, the implications of flash drought are profound and underappreciated. The traditional model of fire season preparation operates on seasonal timescales. Fire agencies assess the preceding winter's snowpack in late winter, evaluate spring precipitation and soil moisture trends through April and May, and develop fire season outlooks that inform resource pre-positioning and preparedness levels for the summer ahead. This framework assumes that the transition from low fire risk to high fire risk happens gradually enough, over weeks to months, to allow preparedness responses to track the developing risk. Flash drought breaks that assumption. A region can go from near normal moisture conditions to catastrophic fire weather fuel conditions in a window shorter than the preparedness response cycle. By the time the flash drought is fully visible in the monitoring data and the fire season outlook has been updated to reflect it, the landscape may already be in the condition it will be in on the worst fire weather day of the year. This is not a theoretical concern for the current situation. It is the description of what has actually happened across the affected states over the past several weeks. The March heatwave arrived. The flash drought process began immediately, driven by the same heat, low humidity and wind that defined the heatwave. Soil moisture and vegetation moisture declined at rates consistent with peak summer evapotranspiration. The fuel preparation that normally takes a full summer season completed in weeks. And the fire management system, calibrated around a fire season that begins in June, finds itself in late March facing fuel conditions that belong to August. The flash drought did not wait for fire season. It delivered fire season conditions on its own schedule, driven by atmospheric physics that do not consult the calendar. What if drought no longer takes months to develop but days? The question sounds rhetorical. It is not. It is a description of documented reality across multiple continents, appearing with increasing frequency, driven by atmospheric conditions that are themselves becoming more common as the climate system warms. The answer to that question changes how we think about fire season, about agricultural planning, about water resource management, and about the fundamental assumption embedded in every preparedness framework that there will be enough warning time to respond before the conditions become critical. The flash drought that assembled the pre-ignition environment across the American West did not announce itself. It did not appear on a map in red until much of its work was already done. It moved at the speed of physics, heat extracting moisture from soil and plant, wind carrying that moisture away, low humidity preventing it from returning, and the monitoring systems watched it happen slightly too slowly to catch it in real time. Tomorrow's conditions are the receipt for a transaction that completed weeks ago, on a timescale the warning systems were not built to match. Part 14. Space weather and atmospheric coupling. This next part requires me to be precise about what is established science, what is active research with preliminary findings, and what is genuine speculation. I am going to be clear about which is which, because the topic is interesting enough to be worth discussing carefully, and it gets misrepresented often enough that handling it sloppily does real damage, both to public understanding of the science and to the credibility of the legitimate questions the research is actually asking. There is a version of this topic that gets passed around in certain corners of the internet that overclaims dramatically in one direction. There is an institutional reflex in other corners that dismisses the entire area of inquiry too quickly in the other direction. The truth, as is often the case with genuinely difficult scientific questions, sits in a more complicated and more interesting place than either extreme. We are currently in a period of elevated solar activity. The sun is not a static object. It is a dynamic, magnetically complex system that oscillates between periods of relative quiet and periods of intense activity on a cycle of approximately 11 years. At solar minimum, the sun's surface shows few sunspots, eruption activity is limited, and the output of energetic radiation and particles is relatively low. As the cycle progresses towards solar maximum, sunspot counts increase, the magnetic field configuration of the sun becomes more complex, and the frequency and intensity of solar eruptions, coronal mass ejections, solar flares, energetic particle events, rises substantially. The current solar cycle, designated Solar Cycle 25, reached its maximum somewhere in the range of 2024 to 2025. By the historical standards of recent cycles, it was an active maximum, more active, in fact, than many forecasters had predicted when the cycle began. The cycle is now in its declining phase, moving back toward minimum, but the declining phase of an active solar maximum is not a quiet period. The magnetic field complexity that accumulates during the rise to maximum takes time to unwind, and that unwinding process continues to produce intense individual events, major flares, significant coronal mass ejections, strong geomagnetic storms, even as the overall activity level trends downward. The most intense individual events of a solar cycle do not always occur at the precise moment of maximum. They occur throughout the active period, including during the decline. During periods of elevated solar activity, the sun releases increased amounts of ultraviolet radiation and extreme ultraviolet radiation across a broad spectral range. It also produces more frequent and more intense solar energetic particle events, streams of high-energy protons and electrons accelerated by solar eruptions to velocities that allow them to reach Earth in minutes to hours. These forms of solar output interact with Earth's atmosphere, and the interaction is not uniform across altitude. The additional ultraviolet and extreme ultraviolet energy is absorbed primarily in the upper layers of the atmosphere, the stratosphere, which sits between roughly 10 and 50 kilometers above the surface, and the thermosphere, which extends from about 80 kilometers upward to the edge of space. The absorption of this additional energy causes measurable heating and expansion of those upper atmospheric layers. This is not a theoretical prediction. It is directly measured by satellite instruments specifically designed to monitor solar irradiance and its atmospheric effects. The relationship between solar activity level and upper atmospheric temperature and density is documented across multiple solar cycles in the observational record. This part of the story is established science. It is not controversial among atmospheric scientists. The question that moves from established science into genuinely uncertain territory is what happens next. Whether the heating and modification of the upper atmosphere by elevated solar activity has any meaningful downstream effect on the tropospheric circulation patterns that govern surface weather. The troposphere is the lowest layer of the atmosphere, extending from the surface to roughly 10 to 15 kilometers altitude depending on latitude. It is where weather happens. It is where the jet stream flows, where blocking ridges form, where storms develop and track. The stratosphere sits above it, and the question of whether stratospheric changes, whether driven by solar activity, by the ozone chemistry that responds to solar ultraviolet, or by the temperature gradients that solar heating modifies, can propagate downward to influence tropospheric circulation, is a question that atmospheric scientists have been investigating seriously for several decades without arriving at a consensus answer. The proposed mechanism runs through the polar vortex, which we examined in detail when discussing the sudden stratospheric warming event earlier in this story. The polar vortex is sensitive to the temperature structure of the stratosphere. Changes in stratospheric temperature, including those associated with solar cycle variability, can, in theory, modify the strength and stability of the polar vortex. A stronger polar vortex tends to keep the jet stream more organized and less wavy. A weaker polar vortex, as we discussed, allows the jet stream to develop larger amplitude ridges and troughs and to hold blocking patterns in place for longer. If solar activity influences stratospheric temperatures in ways that modify polar vortex behavior, then solar variability could, through this chain of mechanisms, have a small but real influence on the surface weather patterns that determine whether a given region receives precipitation or stays dry, whether blocking events form and persist, whether the conditions for extreme fire weather assemble. Some research supports this proposed pathway. Modelling studies have found statistically significant correlations between solar cycle phase and the behaviour of the polar vortex and jet stream over particular regions and seasons. Some observational analyses have found that the stratospheric temperature response to solar variability is large enough, in some seasons and in some regions of the stratosphere, to plausibly influence tropospheric circulation through the downward coupling mechanism. There is a body of peer-reviewed literature, published in reputable journals, that takes this solar influence pathway seriously as a real, if small, contribution to surface climate variability. Other research finds the signal too small to distinguish from the natural variability of the atmospheric system. The atmosphere is a chaotic system. It produces large variability internally without any external forcing, and separating a small solar signal from that background variability is a genuinely difficult statistical problem. Some modelling studies that attempt to detect the solar cycle influence on tropospheric circulation find correlations that fall within the noise level of the models. Some observational analyses find that the apparent correlations between solar activity and surface weather patterns are not statistically robust when examined over longer data records or with more rigorous statistical methods. The scientific community is not in agreement on this question. That is not a failure of the science. It is an accurate description of where the evidence currently stands. What this means for the current situation, for the fire weather event assembling across the American West right now, requires careful framing. The elevated solar activity of the current cycle has been producing measurable effects in the upper atmosphere throughout the period that assembled the pre-ignition environment. Upper atmospheric heating associated with solar cycle activity has been occurring. whether that upper atmospheric heating has contributed, through the stratosphere-troposphere coupling mechanism, to the behaviour of the polar vortex and jet stream that produced the blocking ridge over the western United States. That is a question the science cannot answer with confidence. The mechanism is plausible. The magnitude of any contribution is likely small relative to the forcing from ocean temperatures, greenhouse gas accumulation, and Arctic amplification that we have discussed in earlier sections. But small is not zero, and in a system where the difference between a severe fire weather event and a catastrophic one can come down to the persistence of a blocking pattern by a matter of days, or the wind speed at the critical moment by a matter of miles per hour, small contributions accumulate into outcomes. There is a version of this that gets misrepresented in both directions, and I want to be specific about what misrepresentation looks like here. Misrepresentation in one direction looks like claiming that solar activity caused the March 2026 heatwave, or that the current fire weather setup is primarily a solar phenomenon, or that understanding solar cycles is more important for this event than understanding ocean temperatures or greenhouse gas forcing. None of those claims are supported by the evidence. The primary drivers of the conditions we are examining are the ones we have been discussing throughout this story: the La Niña moisture deficit, the snowpack failure, the flash drought process, the jet stream disruption from the sudden stratospheric warming event, the record ocean temperatures providing the energy budget for anomalous atmospheric dynamics, and the climate change baseline that made the March heatwave 800 times more probable than in a pre-industrial climate. Solar activity is not the story. It is at most a contributing thread in a much larger fabric. Misrepresentation in the other direction looks like dismissing solar variability as entirely irrelevant to surface weather and climate on the grounds that the dominant forcing factors are elsewhere. The dominant forcing factors are elsewhere, but the atmosphere is a system, and systems respond to all of their inputs simultaneously, not sequentially. The solar influence on upper atmospheric temperatures is real and measured. The potential pathway from upper atmospheric temperatures to polar vortex behaviour, to jet stream configuration to surface weather patterns, is physically coherent and supported by some portion of the research literature. Dismissing it entirely because it is smaller than other factors is not more scientific than overclaiming it. It is a different kind of imprecision. The honest position, the one that the evidence supports, is this. We are in an active period of the solar cycle. The sun is doing things to the upper atmosphere that are measurable and documented. Whether those upper atmospheric changes are contributing in some small degree to the circulation patterns that assembled the pre-ignition environment across the American West is a question that atmospheric science has not definitively answered. The answer may be yes, in a small way. It may be effectively no within the resolution of current detection methods. The research is ongoing and the question is legitimate. Are there forces beyond Earth subtly influencing our weather systems? The answer is unambiguously yes. The sun drives the entire energy budget of the climate system. Its variability is a real input into that system. The question of exactly how much its 11-year cycle influences the specific circulation patterns that determine regional weather. That is a question worth asking carefully, worth researching rigorously, and worth discussing honestly. Which is the only way any of this is worth discussing at all. Part 15. The real question. What happens after the first fire? Let me walk you through what tomorrow actually looks like if the ignition gap closes, not as speculation, as a scenario built from the conditions we have now spent the entirety of this story establishing. An ignition occurs. The source does not matter much. A power line arc, a vehicle, a lightning strike from a dry thunderstorm cell moving through the region. What matters is that a fire starts somewhere in the affected area at some point during the peak wind window, when gusts are running at or near 70 miles per hour and the humidity is sitting at 8%. The initial fire, whatever size it starts at, encounters fuel that is at extreme moisture deficit. It does not smoulder. It does not slowly expand. It runs. In high wind fire conditions, fire spread rates can reach multiple miles per hour across continuous grass fuels. In the first hour, a fire that starts along a wind-exposed slope or in an open grass field can establish a front that spans thousands of acres. This is not worst-case speculation. This is documented behaviour from past fire events under analogous conditions. The fire does not wait for suppression resources to arrive. It is already somewhere else by the time the first aircraft is in position. The wind then introduces the spotting problem we discussed early in this story. At 70 miles per hour, burning embers travel, not hundreds of feet, miles. Spot fires can establish ahead of the main fire front in locations that suppression resources have not identified or reached. Now you have 2 fires, potentially widely separated, and then 3. And then the resource allocation problem compounds. Incident commanders have to decide which fires to attack with limited aircraft and ground resources, knowing that every fire they do not prioritize is growing under the same conditions as every fire they do. The resources are finite, the conditions are continuous, the grid stress is not theoretical either. The same wind conditions that create fire weather, stress power infrastructure, transmission lines, distribution equipment, generation facilities. If fire weather produces multiple simultaneous fire events, as the conditions suggest it might, and if those fires interact with power infrastructure, you can develop a cascade where fire damages grid components, grid failures create additional ignition sources, and the suppression response is further complicated by the loss of communication and logistical support that electricity powers. Evacuations under high wind fire conditions present a specific challenge that is sometimes underappreciated. Evacuation routes can become compromised by fire faster than they can be cleared. Communities that have received evacuation orders may find, in the worst scenarios, that the window for safe egress is shorter than the time required to move the population out. This is not a hypothetical, it is documented from past events, and the conditions for tomorrow represent a scenario where fire movement speed would be among the highest on record for March. Here is what I think is worth saying plainly after everything we have examined in this story. This is not a story about whether something bad happens tomorrow. The conditions are what they are, and the probability of significant fire activity under those conditions is high. The story is about what this event represents in the larger pattern. A record heat wave in March, driven by climate change effects assessed at 800 times the pre-industrial probability. A snowpack failure that stripped the West of its seasonal water reserves. A jet stream disrupted by atmospheric dynamics that may be increasingly unstable. Flash drought conditions developing faster than monitoring systems can track. Ocean temperatures providing the energy budget for amplified atmospheric anomalies. And now, at the end of all of that sequence, an ignition environment that has no historical precedent for the month of March. What we are watching is not an isolated extreme event. It is what a connected chain of system changes looks like when they all arrive in the same place at the same time. The heat wave was Act 1, the fuel preparation was Act 2, tomorrow is Act 3. And the question that follows from Act 3, the question that every fire manager, every climate scientist, every utility risk officer and every emergency planner in the affected states is sitting with right now, is not what happens after the first fire. It is what kind of future produces events like this as a regular feature of March, instead of an aberration. Because if the system that generated this event is becoming the new baseline, if the alignment of heat, dryness, anomalous jet stream behavior, ocean energy, snowpack failure, and flash drought is no longer a rare coincidence, but an emerging pattern, then the calendar that tells us fire season starts in June is not just wrong for this year. It may be a document from a different era. And the real work of adaptation is not preparing for tomorrow. It is reckoning with a world in which tomorrows like this one are no longer surprises. The most dangerous thing about what we have been examining is not the fire. It is the possibility that we are still measuring a new reality with the instruments of the old one.